am Tulika Banerjee. Today, I bring you the next learning episode in BSc Forensic Science on an important unit of the paper titled Fingerprints, that is, detection of fingerprints on wet surfaces. In this lecture, you will be studying about detection of fingerprints on wet surfaces. In the interest of solving crime cases, it is pertinent to standardize methods to detect latent fingerprints on such crime scene evidence that have been deliberately or accidentally wetted. There are three techniques to detect latent fingerprints on wet items: multi-metal deposition, physical developer, and small particle reagent or SPR. Each of these methodologies for detecting fingerprints on moist surfaces has both merits as well as demerits. These techniques are being used for detecting latent fingerprints in actual casework investigations. We will wind up this lecture with a conclusion. Let's start our today's lecture with a brief look at what we will be learning today. First is introduction to detection of fingerprints on wet surfaces. Then we have methodologies for detecting fingerprints on wet surfaces, and lastly we have the conclusion. A latent fingerprint is formed when the sweat pores of the papillary ridges leave a deposition of perspiration on a surface with which the finger has been brought into contact. Human body possesses the three types of glands, namely eccrine, apocrine and sebaceous, the secretions of which contribute to a fingerprint deposit. Eccrine glands are widely distributed throughout the body and are particularly numerous on the palms of hands and soles of feet. These glands secrete chemicals as a result of general metabolism and catabolism. Besides water content, eccrine sweat contains up to 1% of the other substances, of which inorganic salts constitute about one half. The other half is constituted by organic products like urea, creatinine, choline, lactic acid, sugars, uric acid, amino acids and proteins. Amongst the organic components of sweat, lipids, fatty acids and peptides are insoluble in water. These are the ones that must be tagged if latent fingerprints are required to be developed on moist items. Such a situation arises if a criminal, after committing an offence, sprays water on the crime scene so as to wash out the finger impressions. If the crime scene is outdoors, there are chances that natural factors like rainfall and humidity may degrade the fingerprints. Under such circumstances, it is pertinent to call into action those techniques that can detect latent fingerprints on crime scene evidence removed from such despoiled sites. There are three main techniques to detect latent fingerprints on wet crime scene evidence. First is multi-metal deposition, then we have physical developer and the small particle reagent or the SPR. These have been discussed here one by one. So, let us take up the first technique, that is the multi-metal deposition technique. Multi-metal deposition is a versatile technique of detecting latent fingerprints on porous items, for example, fabric tape, masking tape, cardboard, on semi-porous items, for example, expanded polystyrene, latex gloves, waxed paper, as well as on non-porous items, for example, metals and plastics. It is named so because it is a two-step process, the first involving deposition of gold and the second deposition of silver on the ridges, thereby visualizing the latent impressions. Next, moving on with the mechanism of this technique. It has been known since long that colloidal gold particles adhere to amino acids, proteins and peptides. The multi-metal deposition technique of fingerprint development relies on the affinity of gold particles for these biomolecules, as the latter are present in fairly large concentration in sweat residue. The methodology is a two-phase process. In the first phase, colloidal gold particles adhere to the amino acid, protein and peptide content of the fingerprint deposition, while in the second phase, silver particles get adsorbed on gold layer, improving the contrast. The process was adopted from a sensitive gold-silver staining procedure, whereby the secondary colloidal silver deposition step improved the labeling of proteins. The colloidal gold particles are produced by the reduction of hydrogen tetrachloroaurate, commonly referred to as tetrachloroauric acid, by the citric acid, and the reaction has been thereon shown on your screen. The working solution of multi-metal deposition method also contains sodium citrate. The citrate anions furnished by sodium citrate engulf the colloidal gold particles and impart a negative charge to these, as is shown in the figure. The amino acids, where R is an alkyl or aryl group, or their fragments in proteins and peptides under neutral conditions, exist as Zwitter ions. However, under acidic conditions, the amino acids acquire an overall positive charge, as has been shown in the figure. Citric acid brings the pH of the working solution in 2.5 to 2.8 range, thereby inducing a positive charge on amino acids present in sweat residue. Thus, the colloidal gold particles bear a negative charge and the amino acids bear a positive charge. The electrostatic attraction between the two chemical entities is responsible for the adherence of gold particles on amino acid, protein and peptide content of sweat residue. It is pertinent to state that citric acid performs two functions. Firstly, it reduces hydrogen tetrachloroaurate ion to colloidal gold, and secondly, brings the pH of the working solution in the desired range. The gold particles adsorbed on amino acid, protein and peptide content of fingerprint residue do not impart a pronounced color to the ridges. Nevertheless, these provide a site for the nucleation of silver particles. The latter are produced by the reduction of silver ions by iron ions. Being a reversible reaction, there are chances that it may proceed from right to left. However, the citrate ions complex with iron ions and remove these from the equilibrium system, pushing the reaction to the right. The silver particles then settle on the colloidal gold, imparting a dark grey or black color to the ridges. Next, we have preparation of reagents. The process of developing latent fingerprints by multi-metal deposition technique begins with the preparation of following solutions. First, we have solution A, and ingredient is 1 gram of hydrogen tetrachloroaurate in 10 ml of distilled water. Second is 1 gram sodium citrate in 100 ml distilled water for solution B. For solution C, the ingredient is 1 ml of polyethylene glycol in 100 ml of distilled water. For solution D, the ingredient is 4.8 grams citric acid in 50 ml of distilled water, that too 0.1 molar. Working solution 1 or the colloidal gold solution is prepared as follows. Place 1 ml of solution A in about 950 ml of distilled water. Mix thoroughly and heat to gentle boiling. Add 15 milliliters of solution B and continue to boil till the contents acquire a port wine color. Turn off the heat source and while the mixture is still hot, add 5 ml of a liquid detergent. Agitate to mix the contents thoroughly. Cool and add 10 ml of solution C. Adjust the pH to 2.5 to 2.8 by adding 1 to 1.5 milliliters of solution D. Make up the volume to 1000 ml. Store the working solution 1 in a clean vial in a refrigerator. Next, the following solutions are to be prepared. Solution E, where the ingredients comprises of 20 grams of silver nitrate in 100 ml of distilled water. Store it in a dark container. Next is 16 grams of ferric nitrate, 44 grams of ferrous ammonium sulphate 11 grams of citric acid and 0.25 milliliters of liquid detergent in 1000 milliliters of distilled water for solution F. Working solution 2 or the modified physical developer solution is prepared in the following way. Add about 10 ml of solution E to 990 ml of solution F. Agitate to mix thoroughly. The shelf life of the solution is just 15 to 20 minutes and therefore it should be formulated immediately before processing the items for developing fingerprints. Process for development of fingerprints. Latent fingerprints are developed by the following procedure. The item bearing latent prints is placed in a tray and covered with distilled water. The tray is rocked gently by using a shaker. The item is placed in another tray to which working solution 1 is added. The tray is shaken for 30 to 45 minutes. If more than one item is placed in the tray, these are not allowed to overlap. The item is taken out of the working solution 1 and rinsed with several batches of distilled water. Faint fingerprints begin to appear. The item is then placed in another tray and working solution 2 is poured over it again. The solution is agitated for 5 to 15 minutes. The item is washed with water several times till the washings are no longer yellow and turbid. The developed fingerprints, which are dark grey or black, are photographed. The item is allowed to dry under natural conditions and thereafter the prints are lifted with the aid of a fingerprint tape. Next, we have the assessment of multi-metal deposition technique. Multi-metal deposition method detects latent fingerprints on a host of surfaces, porous, semi-porous and non-porous, moist and dry. These include paper, glass, adhesive tapes and plastics and polymers. Blood prints too may be enhanced by this technique. However, multi-metal deposition suffers from a number of shortcomings too. It is a costly and a complicated procedure involving several steps. Moreover, it did not give satisfactory results in cartridge cases and interfered with subsequent analysis of firearms. The second technique that we have over here is physical developer technique. The physical developer technique is a means to detect fingerprints on dry and wet porous items including paper articles, clay-based products and adhesive tapes. The process involves an oxidation reduction couple whereby a solution of an iron salt reduces aqueous silver nitrate to finely divided metallic silver. The technique derives its name from the photographic physical developer, which during processing of film rolls undergoes a similar redox reaction. The physical developer reveals the fingerprints as dark grey or black images due to the absorption of metallic silver particles on the fatty acid and lipid components of sweat residue. Then we have the mechanism of this technique. The basis of the physical developer technique is the in situ reduction of silver ions to colloidal elemental silver, which in turn interacts with the organic constituents of the fingerprint residue and ultimately visualizes the impressions as dark grey or black ridges. The same redox reaction is involved in the development of photographic films. The physical developer composition is a mixture of the following components: an aqueous solution of silver nitrate, an iron 2 and iron 3 redox couple, an acid buffer usually citric acid, a cationic detergent usually N-dodecyl amine acetate. The iron 2 ions reduce silver ions to metallic silver and simultaneously gets oxidized to iron 3 ions. Due to the reversible nature of this reaction, the chances are that the iron 3 ions may reoxidize metallic silver to silver ions. To overcome this problem, citric acid is added to the fingerprint composition. Citric acid complexes with iron 3 ions and removes these from the equilibrium system, thereby pushing the redox reaction in forward direction. It also brings down the pH of the composition. This is important since optimum results are obtained under mildly acidic conditions. The finely divided metallic silver particles formed as a result of the redox reaction are colloidal in nature. It is in this state that these adhere to the fatty acid and lipid constituents of latent fingerprint and visualize the impression. However, if the concentration of metallic silver increases beyond a threshold, the particles coalesce and precipitate out. The colloidal nature of silver particles is lost and the quality of developed fingerprints tends to fall. This problem is taken care of by incorporating a cationic detergent, usually N-dodecylamine acetate, in the fingerprint composition. The cations engulf silver particles, imparting a positive charge onto these. The positively charged particles repel each other, thereby averting the possibility of their coming close and condensing into a precipitate. This phenomenon is called as peptization and has been symbolically shown on your screen. Next, we have the pre-treatment of latent prints. The physical developer technique works very well on paper and paper products. However, the finished paper usually incorporates alkaline fillers and binders. These react with the physical developer composition and alter the concentration of its ingredients. It is therefore pertinent to neutralize the alkaline content of paper before attempting to develop fingerprints. This is carried out by giving an acid pre-wash to the paper sample. Malic acid is commonly used for this purpose. The solution containing 25 grams of malic acid in 1 liter of water is prepared. The paper item is dipped in the solution for 5 to 10 minutes till the bubbles cease to evolve. Thereafter, the procedure that I will be describing in the next session for development of fingerprints is followed. Next, here we have the methodology. The following methodology comprises of 3 solutions that are required for detecting fingerprints by physical developer method. The first solution is solution A, or the detergent solution. It is prepared by dissolving 0.23 grams of N-dodecylamine acetate in 40 milliliters of distilled water. Solution B, or the redox solution. It is prepared by adding successively 30 grams of iron nitrate, 80 grams of ammonium iron sulfate, that is Mohr salt, and 20 grams of citric acid to 900 ml of distilled water. Solution C, or the silver nitrate solution. It is prepared by dissolving 10 grams of silver nitrate in 50 milliliters of distilled water. The solution is stored in a dark place. The working solution is prepared as follows. Solution A is added to solution B. The mixture is stirred for 2 minutes. Thereafter, solution C is added and stirring is continued for another 1 to 2 minutes. Before proceeding further, the authenticity of the working solution ought to be checked by the following test. A drop of dilute gold chloride solution is spotted on a Whatman filter paper. The latter is immersed in the working solution. If the spotted region gets darkened within 3 to 5 seconds, the solution is appropriate for use. Otherwise, a fresh lot must be prepared. The working solution is next added to a glass tray, which in turn is mounted on an electric shaker. The object bearing the latent fingerprints is immersed in the working solution, which is then gently agitated by the shaker for about 15 minutes. The tray should not be overloaded with samples. Preferably, only one item should be processed at a time. Dark grey or black colored fingerprints develop. The object is thoroughly washed by immersing it in distilled water for 5 minutes. The washing operation is repeated twice more, each time with a fresh batch of distilled water. Next, we have assessment of physical developer technique. Physical developer is a sensitive method of detecting fingerprints on porous items. It is specifically useful when fingerprints are required to be visualized on articles which have been deliberately or accidentally wetted. Under these conditions, the amino acid constituents of sweat residue are easily washed out and ninhydrin method fails. Nevertheless, physical developer yields results. The sensitivity of the composition may be enhanced by pre-treatment and or post-treatment methodologies. However, the requirement of a relatively large number of reagents makes the technique cumbersome and expensive. The third technique that we are going to study is about a small particle reagent or the SPR technique. A small particle reagent technique is used to detect latent fingerprints and non-porous crime scene evidence, including those that have been accidentally or deliberately wetted. Conventional small particle reagent is formulated by suspending a finely powdered insoluble binary salt, usually molybdenum disulfide or titanium dioxide, in water containing a few drops of a surfactant. A commercial liquid detergent is generally used as a surfactant. The insoluble salt adheres to the fatty components of the sweat residue. The small particle reagent technique is also referred to as wet powdering. What is the significance of this technique? The most common base material used for formulating a small particle reagent is molybdenum disulfide, that is MOS2. MOS2, an insoluble binary inorganic salt of dark grey shade. When suspended in water containing a few drops of a surfactant and applied to a latent impression, the salt gets absorbed on the sebaceous constituents of sweat residue. The salt is pulverized before preparing its suspension, and hence the technique is often referred to as wet powdering. The particle size in the range of 1 to 10 micrometer is deemed appropriate for detection of latent impressions. The crystalline structure of molybdenum disulfide too is critical for developing optimum quality fingerprints. Base materials like titanium dioxide, cobalt oxide, graphite and photocopier toner may substitute for molybdenum disulfide. The sebaceous sweat largely contains fatty acids, lipids and glycerol derivatives. These biomolecules are quite stable and retain their composition in latent fingerprints for relatively long periods. Moreover, they are insoluble in water. For this reason, a small particle reagent is able to detect fingerprints on those items which have remained immersed in water for varying time periods. The method has been used to detect fingerprints on vehicles wet with rain or on glass, metal and plastic items recovered from aquatic systems. It has also been used to develop fingerprints on water-soaked firearms. The detection process does not interfere with subsequent ballistic analysis. The small particle reagent method has also been used to detect latent fingerprints on raw ivory articles. In addition, it works on plastic bags, wax paper, glass and painted utilities. A small particle reagent method works on containers which become contaminated by the commodity they hold. For example, soft drink cans and glasses are often wetted by the beverage. Regular powders fail to detect fingerprints on such surfaces, but a small particle reagent technique gives results. The powder method often fails to develop fingerprints on items which have a rough texture or an irregular shape. The reason is that the powder cannot be brushed to every nook and corner of such a surface. Yet, when the article is treated with a suspension, either by dipping or by spraying the composition, it touches every segment of the surface and chances of detecting fingerprints are far greater. The molybdenum disulfide based small particle reagent has been successful in lifting latent impressions from glass bottles coated with arson accelerators, including gasoline, diesel, turpentine oil and thinner. The surfactant, also called as surface active agent, is an important component of a small particle formulation. It has two functions. Firstly, it delays the sedimentation of the insoluble salt, and secondly and more importantly, it ensures a uniform application of suspension on the surface. Usually, a commercial liquid detergent serves as a surfactant in small particle reagent formulations. Its concentration in the composition is critical to optimum development of fingerprints. If it is too little or too excess, the quality of prints is lowered. The fingerprints developed by molybdenum disulfide based composition are dark grey in color. Proper contrast is not achieved if the background color of the surface too is dark. For such surfaces, molybdenum disulfide is replaced by titanium dioxide or TiO2. Since titanium dioxide is white in color, it gives a good contrast on dark surfaces. In fact, the titanium dioxide based composition gives clear and sharp fingerprints on adhesive materials. Next is the methodology. Small lots of molybdenum disulfide, that is 7.5 grams, are added to water of 75 ml and a commercial liquid detergent taken in 0.3 ml or 2 to 3 drops, for example that of Gentle or Easy. The suspension is agitated and transferred to a tray or a spray bottle. The surface bearing the latent fingerprints is either sprayed with or dipped in the small particle reagent formulation. On vertical surfaces, the reagent is sprayed directly above the region where fingerprints are likely to be present. As it drips down, it covers the latent impressions. It takes 1 to 3 minutes for the fingerprints to develop. Thereafter, the item is washed under a gentle stream of water for about 30 seconds to remove the excess material. The developed fingerprints are photographed. These are then allowed to dry either under natural conditions or with the aid of a hair dryer. Finally, these are lifted by using the fingerprint tape. An advantage of a small particle reagent technique is that after the fingerprints have been photographed and lifted, the surface may be rendered clean by wiping with moist cotton. No permanent stains are left on the surface after impressions have been developed. Next, we have the assessment of a small particle reagent technique. A small particle reagent is an efficient and sensitive technique to develop fingerprints on wet, non-porous items. It gives good results even on dry surfaces. The method is simple and may be operated even by an amateurish hand. The three techniques, that is multimetal deposition, physical developer and a small particle reagent, which has been outlined in this lecture, serves to detect latent fingerprints on wet crime scene evidence. Whereas the multimetal deposition and physical developer method are used mainly for porous items, the small particle reagent or the SPR works on non-porous articles well. The multimetal deposition and physical developer procedures are cumbersome and time consuming. Both involve a large number of steps as well as a large number of reagents. Moreover, the methods are expensive. The small particle reagent technique, on the other hand, is simple to operate. It requires fewer reagents, gives quick results and is cost effective. With all these information, here we come to the end of today's lecture. Do keep in mind what we have discussed today. I'll be back with one more lecture in the series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I'll see you in the next lecture. Have a great day.